Okay, we're going to talk today about black oil PVT, and this is covered in chapter 6. And briefly, we've been discussing flash calculations and the last week or so. There will be a problem posted on doing these flash calculations this weekend. And in connection with that, one of the main applications is a multi-stage separator test, whose main purpose is to generate from a producing well stream, if you will, with composition ZWI. The W is for well stream coming out of a well, and to see what that well stream will create in terms of sellable products in dollars per barrel and dollars per 1,000 standard cubic feet, or whatever units you want to use. So sellable volumetric products. Basically what we refer to as G surface gas and O at the hat stock tank oil, surface oil. And so this is a natural lead into the black oil PVT formulation, because the black oil, what it really means is that we're going to treat the reservoir mixtures in terms of two components instead of methane, ethane, propane, and so forth. So essentially it's going to uses two, I'll call them pseudo components because they're not really components, to describe the gas and oil phases at whatever pressure and temperature we're interested in. It might be reservoir pressure and reservoir temperature. It might be within the production tubing or wherever, but the point is that we're going to use two pseudo components to describe the gas and oil phases instead of what we've been talking about, a compositional, meaning nitrogen, CO2, methane, ethane, and so forth out as far as you want to go, maybe C7, maybe out to C, 35, and then heavier. Who knows? That's typically what, if you send a sample to a PVT laboratory today, they'll typically give you a compositional description of that sample out to somewhere between C25 plus and C35 plus. So they'll give you all this information about the compositional. And instead of using that directly to describe in an equation of state or the Wilson K values to describe the phases, the compositions of the phases, and the properties of the phases instead of doing that, because it's a real pain in the butt, and particularly when this black oil method was starting to be used way back in the 40s and 50s and 60s, we didn't have computers to do the kind of things we can do today with an equation of state. So there's a history, there's a convenience, and even today with the computers, you guys are going to be, in a sense, happy to use this simplified approach to describe your gas and oil with 2 components instead of 22. Okay? But that's essentially what the black oil PVT formulation is. And then the question is, what are the 2 pseudo components? So these 2 pseudo components are surface gas, our symbol being G, and surface, or stock tank, whatever you want, oil, O, resulting from some kind of multi-stage process of the actual well stream through some 2, 3, 5 stage, whatever it is, process to create these 2 surface products. And we're going to say that these 2 products, we can treat them as pseudo components, and if we can figure out how much of those 2 products are in the reservoir gas, the reservoir oil, or the oil and gas in the tubing, then we've done our job. And we're not going to talk about moles or mass of these pseudo components. We're going to talk about volumes. Okay? So, and we use volumes instead of moles. Okay? So that's another characteristic of the black oil model. And these 2 components are results of a specific surface process, which I'm going to be writing like this. A capital P with 2 lines under it means that it's a complicated surface process, okay? But instead of sketching the process or doing something else, then that's what I mean by this process. This can be, maybe I'll put a box around here or something, that it's hidden all the complications behind it. Okay. In last lecture we talked about taking in basically a composition and separating it in multiple stages, where each stage, the oil from each stage, was further processed into, I think we did 3 stages, and we end up with our surface oil here. And if we take all of the gases, this is the surface gas from stage 1, and this is the surface gas from stage 2, and this is the gas from stage 3. If we just add those 3 gases together, then we get the total surface gas from that. And this process box, or the capital P, is essentially just the kind of, you just create a box around all of this stuff here, and inside it, it might be 3 stages or 4 stages or who knows what. You go in and you come out with these 2 amounts, and the amounts that we come out with will be in volumes. Even though when we did the flash calculations last lecture, we got moles of gas and oil. But remember, we had the conversion through the density and molecular weight. We converted the moles to volumes. Okay. How many have ever worked with the black oil table or formulation? Some of the international students maybe have, or not? A little bit? Okay. So Now this composition here that we've got, if we take that mixture and say that it is single phase. So we're now going to say that if it's single phase at a particular pressure and temperature in the reservoir, in the tubing, wherever you like, okay? At the pipe just entering the process. It could be right there, okay? It is still that mixture. But if it happens to be single phase, then it will have a volume, correct? At pressure and temperature. And that also comes into our black oil formulation. And we're going to label the phase gas or oil, right? According to what? According to our pressure temperature diagram, okay, which is kind of a pseudo label unless it's right on the saturation, the bubble point. Unless P and T is on that line, the bubble point line, we don't really know if it's an oil or a gas, or on the dew point line. But we're going to use this pressure temperature diagram in a sense to, and so we're gonna label this single phase as either gas or oil. Okay? And if I ask you on the exam, how do you label what the phase is? You say, well, you take this composition, you do a pressure temperature diagram, you color in green, you color in red, and then you don't really need the rest of this, but if you do that, then it will depend where the temperature is relative to that critical point. Okay? And if my pressure is up here, but my temperature is down there, what do we call this phase? An oil. Okay? And if it happens to be at this pressure over here and that temperature, what do we call that phase? That's a gas. Okay? So you have to have a composition, you have to have some, pressure temperature diagram, or maybe its density is 800 kilograms per cubic meter, and you can just say it's oil-like, okay? So I call it an oil. But if it's got a density of 400 kilograms per cubic meter, you're going to start scratching somewhere, some body part, not being sure what phase it is. Okay? Okay, so this dashed line is what I'm going to refer to as a process, something like that. We've got products, two pseudo components, surface gas and surface oil. They're quantified not with moles but with volumes. So for example, standard cubic meters or standard cubic feet, standard cubic meters or stock tank barrels, typically. In addition to that, we have that mixture assumed to be a single phase of type gas or oil at some pressure and temperature, and it will then have a particular volume. And I'm going to label it V of PT, but I'm also going to put a label of phase. Okay? And I'm just going to put a generic P here. It's probably bad. This is not in the book. It's either G or O, all right? Okay, it's got a phase identifier. Gas or oil. All right? Any questions? Okay. Now, the black oil PVT model uses volume ratios. Not volumes directly. It uses volume ratios to define its PVT phase and volumetric behavior. Phase and volumetric behavior. So instead of composition, which is our compositional phase behavior quantities, molar amounts of each phase, okay, and Fg, if you will. These are kind of the quantities for compositional effect. And volumetric behavior would be, well, that would be oil values. So instead of this compositional, it will use volume ratios. So instead of mass, moles, and densities, which is the normal, this is all in a compositional environment, where we use these quantities to describe the phase and volumetric behavior of mixtures. Instead, we're going to use volume ratios. Okay? And now I'm going to define, there are two fundamental types of volume ratios. Okay? Type 1 is surface volume ratios. Okay? And there are two of them. There's capital RS and it's defined as the surface gas volume divided by the surface oil volume, where the mixture Zi, the mixture we're talking about, is an oil phase. In other words, this Zi is representing an oil. Okay? For an oil phase. So if you see RS, it is telling you something about the oil phase, not about the gas phase. Okay? And the second ratio is little rs, and it's defined as the surface oil volume divided by the surface gas volume. Oh, that looks just like the inverse of rs, but it's not. Because it is this ratio where the mixture we're looking at is for a gas phase. Okay? It's for a gas phase. So if you see little rs is equal to 100 stock tank barrels per million standard cubic feet, or 400 standard, that's not used, yeah, 400 standard cubic meters per million standard cubic meter. If you see a number little rs, it's telling you something about a gas phase. Okay? Now, you can see you can start getting confused, because you say, well, the one definition is a Vg over Vo, and if I just take the inverse of that, I get what you say is little rs, but you're saying it's not the same. It's not the same thing. Okay? You're saying that rs is not equal to 1 over little rs. Okay? And it is because of this. Okay? So to bring clarity to this, in chapter 7, I told you that wrong already. This is my first of many mistakes today. This is chapter 7. Okay. Chapter 7, that book, in this book, Chapter 7, it's probably the first place ever that they use differentiating nomenclature to avoid this confusion. Okay? All right? It's the first time. Now, a few other people in papers and books have used it later, but not really. But the point is, to avoid this confusion, we now use a nomenclature that looks like this. We say that the surface gas volume is derived from an oil phase. Okay? So it's written VG hat O. And VO hat oil says that the surface oil, oops, that's wrong. The surface oil is coming from an oil phase. Okay? Yeah.
Is it the phase that we take for the ZI?
That's right. Whatever you find out your ZI is, if it's here or if it's here. If it's on the right, if it's a gas phase, and you process that through the process and you get a surface gas volume and a surface oil volume, then you will use those two to calculate little rs. Because it's coming from a gas phase. But if what you're sending into this process is over here, it's an oil phase, you put it through the process, you get a surface gas volume and a surface oil volume, you're not going to calculate little rs with that, right? You're going to calculate big rs. Because it's a gas phase, surface gas, it's a surface gas coming from an oil phase. And the little rs is a surface oil coming from a gas phase. And it's a surface gas coming from a gas phase. Okay. And now it's easy to see why big rs is not equal to 1 over little rs, because we don't have the same terms, right? So this is okay. We understand that now. But without these extra terms, Curtis is just saying more crazy stuff again. Friday, the 28th. But now we have a way of saying that, well, it's okay. A little bit of what he says makes sense. So that's the first kind of surface, or that's the first kind of volume ratio. It's a surface volume ratio. One for the oil phase and one for the gas phase. And in reality, these terms, or these quantities, are the pseudo equivalents. That's the pseudo equivalents of xi, mole fraction, which is, in a sense, the oil phase composition, and the gas phase composition in molar terms is yi, and that is basically being represented as a volume fraction. That's a wild looking y. So the little rs is, in a sense, telling you the how much surface gas and how much surface oil I have in a volumetric ratio. So it doesn't sum to 1 in a sense, but it's, in a sense, giving you that information. These are the pseudo equivalents. Okay. So these two terms, rs and little rs, whenever in the rest of your 40-year career you're working with a solution GOR, maybe working with a solution OGR, oil gas ratio, big rs and little rs, I want, pray to God, that it'll be burned into your mind that you're actually talking about a composition. You're kind of saying, of this reservoir gas, how much surface oil condensate will I get and how much surface gas I will get. And why will that be important? Why do I want you to remember that? I want you to remember it not because I want to brainwash you. Because I think it's important, you should think it's important. That's not the way it works. Because what you think is important, I probably don't think is important all the time. Okay? But you guys in the next 40 years want to get paid your salaries, right? And the salaries come from revenues. And the revenues come mostly from surface oil, right? So knowing you got some mixture in the reservoir, knowing how much is going to end up giving you $116 a barrel and how much is going to end up giving you $3.50 per MCF is going to affect the bottom line of the company you're working for. Maybe it'll be your oil company. Maybe you'll be getting directly the revenues, and you sure as hell want to be interested in knowing what's oil, surface oil, sellable oil, and what's surface gas, okay? It is not because Curtis is a crazy PVT guy, okay? It affects your getting paid, in a sense. Or maybe when you go to ask for a higher salary, you can say, excuse me, boss, but do you have any effing idea how much more surface oil, how much more revenues we're putting in the tanks, because I understood how to get more out into the surface oil and the surface gas, and my little RS is bigger than the previous guy. I want a salary increase. And your boss is just going to look at you. You're going to have to explain it to him 3 or 4 times, or her maybe, but finally you'll get across. You multiply the 116 by, and all of a sudden the boss says, yeah, you get a raise. Okay? So that's why I want you to understand this. Now, I can say they're equivalents. You actually can compute the mole fraction. Okay, we can actually compute the mole fraction from this surface volume ratio. And I just to show you, it's not really a pseudo equivalent, but it actually is an equivalent. Okay. So let's say we have our components are G and O, okay? And let's say that we know, in addition to the volume ratio, we know the molecular weight of that and its density, okay? So all I'm asking is for 2 pieces of extra information, and I can make this translation between the surface volume ratio and actual mole fraction in terms of 2 components. So let's just do that exercise to see that I'm not smoking dope. Okay? So this is the way we're going to do it. So what we have, and let's just take for oil, so we're going to go from here to here, and what we have is VG over VO coming from oil. Okay. Okay, so what we're going to do here is this. We're going to take and multiply. First we'll start with the oil. We're going to multiply, and by the way, you have to have this surface oil coming from the reservoir oil. If we multiply the volume down here with the density, okay? Ecofisk, first big discovery, about 850 kilograms per cubic meter, okay? And now I've converted my volume of surface oil, and I'm going to do this in metric units. So I'm going to say we start with standard cubic meters per standard cubic meter, which for Ecofisk, since I started talking about Ecofisk, is about 300 standard cubic meters per standard cubic meter, RS, just to have a number. And this was around 850, I think, kilograms per standard cubic meter, and the molecular weight was pretty close to about 200 kilograms per kilogram mole. Okay, so now I've got the ratio. That ratio is 300, Okay, so this ratio is 300. Okay. I'm going to have to divide by the density. That gives me on the bottom, it gives me what? It gives me mass. And then if we take and multiply or divide by the molecular weight here, that will give us moles, right? So now on the bottom we've got moles. Okay. Do we agree? Now, how do I convert the surface gas volume to moles? There's some magic number out there. Any surface gas volume, 23.68. So we have to divide this by 23.68, and that's in kilogram. That's in standard cubic meters per kilogram mole. Okay, and that gives us surface gas moles coming from the oil. So at least directly we can calculate the ratio of moles of surface gas to surface oil, right? That's a starting point. It's not X of I, but it's a starting point. And in our particular case, that would be 300. You'll move the molecular weight on top. That was about 200. And down below here, we've got 850 and 23.68. Okay? And that's a molar ratio. It's not mole fraction, but it's a molar ratio. So it doesn't have any units. And it's around 0.03. Somebody can calculate that for me, but calculator, please. It's something like that. But mole fraction is going to be, for example, the mole fraction of the gas component would be this divided by this, correct? I'm still waiting for the number. Well, that's pretty damn close to 3. I mean, I give myself, I don't know how I got that, but pretty close to 0.03. Sometimes it works and sometimes it doesn't. I have to tell you a short little story. I can do things like that, but I can't get on a train in the Netherlands and find one of the world's largest airports. I got on the train from this Groninger. Groninger is close to the Groningen field. It used to be, maybe it had the largest gas reserves in Europe before Troll. Maybe it's bigger than Troll, but it's old and it's emptied. And there was a conference there, and I got there thanks to some lady at the airport. She bought the ticket for me. Well, she didn't pay for it, but she showed me on. She pointed the direction, so I got on the train. I got to the conference, and I was going to come back. I get on the train, and then I don't fall asleep, but I'm ignoring everything going on. And along the way, they're going to change the train driver. The train driver doesn't show up. He's been drinking too much the last night, so they decide to send this train somewhere else. Of course, everybody but me gets off, who's supposed to take another train to the airport, and I'm sitting there, and after 2.5 hours, I'm supposed to be at the airport. I go to the guy, some guy standing there. I said, "Are we close to the airport?" He says, "The airport's way the hell over in the other part of the country." So I don't know. It's terrible. It's embarrassing, but it's true. So the 0.03 was pure luck. But we've got the ratio of the moles, and the mole fraction, which I'm trying to convince you can get, is just the ratio of the surface gas moles over the total moles. But that we can rewrite in this way. We can say that that's equal to NGO. And now I'm going to divide top and bottom by the same thing. I'm going to show you what I'm doing. 1 over NOO. 1 over NOO. So we've got NG over NOO plus NOO over NOO, which is, yeah, we got that one figured out. We agree? I'm just going to call this thing up here, well, I have to be careful. Well, let's just call it 0.03. Okay. So this is NGO, NOO, NGO, NOO plus 1. Okay? And then to make it a little bit more convenient, I'm just going to do this. I'm going to divide everything by that ratio. 1 plus NOO over NGO, which is the inverse of this RS, right? Or it's the inverse of what we did here. Well, this term here we can show from above is just 1 over RS, and now we'll put the 2368 on top, and we also need to put that on top. Is that term there? If I did it right. Because this term here was our RS, and then did I do that right or not? Should be 1 over RS, yeah. And then we we take it upside, we get the 2368 on top. We get okay, I think this is right. Which means that X of G, mole fraction of the surface gas component in the oil phase, is just 1 plus 1 over RS times this constant. To the minus 1. Exact. I mean, that's the mole fraction. So you can see that is the mole fraction. I mean, so if you've got RS, you can get mole fraction. And then the mole fraction of the other component is what? We just make our life easy and just write it like this. Okay? So it also is a function only of RS. RS, standard cubic meters per standard cubic meter, rho, kilograms per cubic meter, and molecular weight is given by God, kind of. Okay. Now I say that is given by God, or I don't know, some society that says this is the way it should be, that the mass should always be associated with a certain kind of mole, which is connected to the mass, right? So that methane always has 16 as a molecular weight. That's the way it's supposed to work. In the civilized world and in the uncivilized world, that's the way it's supposed to work. The molecular weight of air is always 28.97, unless it's really bad air. It might be different. But Schlumberger, who everybody knows about, right? Everybody heard of Schlumberger? They buy free pizza and Coke or beer. Yeah. They're the biggest service company in the world. Do you know who the president of the Schlumberger company is now? What's his name? Yeah, and you know where he comes from. Yeah, he used to listen to my damn lectures, you know. See, the future is yours, you know. He's at the top because well, probably not because he sat on my lectures, but he used to be one of you guys. He's the president. But he's the president of the company who says, well, God, I mean, that's a relative thing. Molecular weight of methane doesn't have to be 16. So in their PVT reports for the last 15 years, and I know it's 15 years because they sent one of their lab personnel to one of my courses about 15 years ago, with version 0.1 of the new Schlumberger software, PVT software. And in that, the guy says, would you, Curtis, be kind enough to give me feedback on this report? So happy. New software-generated PVT report. So I start looking at it, and everything looks kind of okay. And then all of a sudden, I see that they have molecular weight listed in 2 units. Grams per gram mole and grams per pound mole. And it wasn't any longer 16, the molecular weight of methane. I come back to him the next day or whatever, and I say, I don't think we want to go here. This units thing is, field units are bad enough, but you don't want to give molecular weights in grams per pound mole. But it's still there in their software, so I think it's still there. At least it was there for 10, 12 years. I used to raise hell about every course I would tell about how there was God and there was Schlumberger, and it was like, and I'm still telling you the story. So maybe they have changed it, probably not. So anyway, so you have to be a little bit careful. But anyway, it should be molecular weight is in a kind of a consistent unit. So we've shown that the surface volume ratio can be translated into mole fraction, and effectively it's giving you the composition of your oil phase in terms of the 2 components, surface gas and surface oil. Okay? And I think you get the same equation if you want to know in the gas phase what is the surface gas mole fraction. I think you end up with the same equation, 1 plus little rs directly times 23.68. But now it's the surface oil density of the surface oil coming from the gas. And in Equifisk, when you finally got some gas coming out of the oil, its surface oil density was not 850. It was 650. Okay, so it's a different surface oil. Okay. And we'll just make a little footnote before the break that the surface oil from an oil phase is physically not going to be the same surface oil from a gas phase. And that's discussed in detail in Chapter 7, OG. Anybody heard the Phantom of the Opera, not movie, but Phantom of the Opera musical? Anybody heard, seen it? It's really a great. If you're going to go to New York or London or somebody, that's where you want to go. And that's one of the songs has this OG, in it. But it means opera ghost, and it's the phantom. It's a nickname for the opera ghost, OG. So I see that way. It's also in Norwegian for the non-Norwegians. It's the word for and. This is OG. This is the word for and. So now we have a problem, or not really a problem, but physically these are not the same. But in our use of black oil PVT, we use the assumption, and it's not particularly a good assumption, that all the properties are the same. Density, you don't really use molecular weight, but that was just for our exercise. I'll just put that in parentheses. Okay, this is actually used in our engineering calculations. This is only used if we want to do this mole fraction conversion. But the point is that it makes this assumption, and it's a particularly bad assumption. It's not a very good assumption. Okay? So it's not particularly good assumption. And this also assumes that these are the same. It's not as bad as the oil assumption, but in the case of here, the density of surface gas is assumed to be the same as the density of surface gas from both phases. And this is used in our engineering calculations in this black oil model. And it's usually just kind of so-so. It's not as bad as the oil, but it's just so-so. So we make this assumption, but in reality those are not equal. Okay? So we're due for a break here. Any questions before the break? Okay. We can take them after the break.